Okay, so in this lecture, we are going to introduce the notion of a normal operator and a self-adjoint operator. In the previous lectures, we had established the concepts of inner product spaces, adjoint operators, and most importantly, the concept of an orthonormal basis. The concepts of orthonormal basis will be studied throughout the time we will be studying such operators, because whatever we are dealing with, whatever correspondence we will be having to establish between operators and matrices, everything will be done with respect to an orthonormal basis. So let's give the heading normal and self-adjoint operators. Okay. So what are we actually trying to do is that we want to establish the concepts of diagonalization, at least a necessary condition for diagonalization. I shouldn't say a necessary condition for diagonalization. We will eventually see why we try to include the concept of diagonalization in this lecture, but there will be something related to diagonalization of complex and real matrices specifically. There will be a slight difference between them. And to establish the concept of diagonalization, first thing which we will be dealing with is the concept of upper triangular matrices. Concept of upper triangular matrices. So yeah, I don't think we need any more discussion. Let's get straight into the discussion we want to do in this lecture. So we start with a lemma, and throughout this lecture we are gonna deal with the concepts of eigenvalues and eigenvectors that must have been already precise, because we are gonna include the concepts of diagonalization and upper triangularity of matrices. The lemma is as follows: that if I consider a finite dimensional inner product space and linear operator on it, then the linear operator, if the linear operator has an eigenvector, so does its adjoint. Okay, so let T be linear operator on V, where V is a finite dimensional inner product space. Then I want to say is that then if T has an eigenvector, so does T star, that is the adjoint of T. Okay, how do we deal with this? Proof. So we start with an eigenvector of T. That's quite precise, right? Because we need to consider that T has an eigenvector to show that its adjoint has an eigenvector as well. So suppose T has an eigenvector. Suppose T has an eigenvector, let's say corresponding to an eigenvalue lambda. Okay. Now by the definition of an eigenvector, it is surely non-zero. So let the eigenvector be x, which is obviously non-zero by definition. Okay. Or let it be v, because we will be denoting an arbitrary element by x. That's more conventional a method. Say v. Then for all x in v, see, we can write 0 as the inner product of x with 0 or 0 with x, whatever. But then I can write this as, I can write the 0 as t minus lambda I of v and x. Right? This straight away follows from the definition of an eigenvector corresponding to an eigenvalue lambda. But then I can use the adjoint. So I can write it as v with t minus lambda I star x. But surely enough, I can distribute the adjoint inside to get t star minus lambda bar I. This we have seen in the previous lecture, and it's mapped with x. So we have this sort of an equality. See, this immediately means that therefore V is orthogonal to all the vectors which are of this form, right? It's orthogonal to all the vectors of this form, right? But the collection of all the vectors of this form are precisely the range of the operator t star minus lambda bar I, right? So V is orthogonal to the subspace range of t star minus lambda bar I, right? Now we know that a certain linear operator will be onto or surjective if its range equals the vector space on which we have defined the operator. We also know that we can write a vector space in terms of a direct sum of an arbitrary subspace of it and the orthogonal complement of that subspace. Surely enough, if V is orthogonal to the range of t star minus lambda bar I, this implies that the orthogonal complement of t star minus lambda bar I is non-empty, but that surely means that the range of t star minus lambda bar I won't equal V, but that surely means that t star minus lambda bar I is not surjective, right? But if it's not surjective, then surely it's not injective as well, because V is a finite dimensional space. So this implies T is not injective. How does it follow? Since V is finite dimension, right? So this typically means, so since T is not, so since this operator T star minus lambda bar I is not injective, its null space is non-empty, right? Its null space is non-zero, right? This implies the null space of T star minus lambda bar I is non-zero. So suppose therefore let say V dash be an element from the null space of T star minus lambda bar I, and we choose this V dash to be non-zero because that surely exists now. But observe, this implies T star V dash is same as lambda bar V dash. So this implies that V dash is an eigenvector of T star, right? Therefore, if T has an eigenvector, T star also has an eigenvector. So we have precisely established that fact, right? Clear? This leads us to a very important theorem which we will be later using to characterize the concepts of diagonalization in terms of operators, which is the Schur's theorem. So it's called the Schur's theorem. Okay. What does this say? This statement you might have seen in some previous lecture as well, when we were discussing diagonalizability and diagonalizability in terms of minimal polynomials. This topic is covered in my playlist, important topics on linear algebra, where we had said that if we consider an operator on a finite dimensional vector space such that the minimal polynomial of that operator splits, then the operator is the matrix of the operator is upper triangular with respect to some ordered basis, right? In this case, we will be too specific about a basis. We will say that let T be a linear operator on a vector space G such that its characteristic polynomial splits. Okay. Then there exists an orthonormal basis. Then there exists an orthonormal basis, say beta, such that the matrix of T with respect to beta is upper triangular. Obviously, this orthonormal basis will be a basis for V. That's nothing to be mentioned specifically. Okay, so we're going to prove the statement. Okay, see, if the characteristic polynomial of T splits, then so does its minimal polynomial, right? And so does its minimal polynomial. If it's minimal polynomial splits, then what I said is that there exists an ordered basis. This implies there exists an ordered basis beta such that beta is equals to say w1, w2, and so on and so forth till wn, such that, so there is an ordered basis beta where I define beta to be like this, such that the matrix of T with respect to beta is upper triangular. Right? Clear? Okay. Now what we do, which is quite, I guess it's quite intuitive from the here, that we simply apply the Gram-Schmidt orthogonalization to this basis beta. So we apply the Gram-Schmidt orthogonalization to beta to get an orthonormal basis. Say beta dash, which is equals to say v1, v2 till vn. Clear? Yeah. Now, see, when you studied the concepts of the Gram-Schmidt orthogonalization, there we had said that if I start up with a basis beta and I choose out any k vectors out from that, then after applying the Gram-Schmidt orthogonalization, the first achieved orthogonal vectors from the basis, the span of the first k achieved orthogonal vectors from the basis will be same as the span of the first k vectors from the ordered basis we started with. Okay. So now suppose I consider sk to be the span of the vectors w1 till wk, and I take sk dash to be the span of the vectors say v1, v2 till vk. Let us now consider only an orthogonal basis. We can later orthonormalize it, right? An orthogonal basis. Clear? Okay. Yeah. This is a elementary fact that we can sort of establish an equality between the span of sk between sk and sk dash. Okay, we will surely talk about that. Or let me be a bit precise. Let me just define sk to be these vectors. Okay, then I'll use the span of sk and sk dash. That will be better, I guess. Now recall this fact. Recall that let beta. So this is abuse of notation. I've already used beta. Let me say let gamma be the vectors v1, v2 till vk, such that the matrix of T with respect to beta is upper triangular. Or let me write it like this. I can establish an equivalence of what I'm trying to say. Be an ordered basis for V, and let T be a linear operator on V. Let T be a linear operator on V. Then the matrix of T with respect to gamma is upper triangular if and only if T of Vj is in the span of the vectors v1 till vj. Okay, and this happens for all j is equals to 1, 2 till n. Okay, now how does this typically follow? Okay, I hope this is not a difficult thing to establish. You can prove it on your own. You just need to get hold of a upper triangular matrix, and then you can find that it trivially holds equivalently. Because let me just give a hint to it. Suppose, so what will be T of V1? So T of V1 will be in the span of V1. So I can write T of V1 as say some A11 times V1. But then what will be the coordinate matrix of T of V1 in terms of the basis V1 till Vk? It will be just A11, right? And all the other elements in the column will be 0. The first element will be A11, all the other elements will be 0. On a similar way, if I consider TV2, then I'll get two specific coefficients along the column, say a 2 1 and a 2 2. And in see, if you proceed in this way, you will get a upper triangular matrix. And the converse is trivial, right? If you start with an upper triangular matrix, then you just consider the linear operator induced by T, and it will do the job. There's nothing too difficult to establish here. Okay, so now we can use this fact. See, uh, so we have defined Sk to be this set of vectors and Sk dash to be this set of vectors. Since Wk is in Sk, therefore T of Wk should be in the span of Sk. Okay, clear? Okay, and this happens for all k. Okay, yeah, that will do, I guess. Now, span of Sk will be same as span of Sk dash, right? So this implies T of Wk will be a vector in span of Sk dash as well. Okay, and let's say for all k. But then, since each Vi comes from each Wi's using the Gram-Schmidt orthogonalization process, therefore we can say that T of Vk, this is also contained in the span of Sk dash, right? Right. But if T of Vk comes from the span of Sk dash, then that typically means that the matrix of T with respect to B dash is upper triangular. Okay, this follows from this, the statement we wrote. Okay, is it clear? This follows because Wk, so I just said a misstatement that Wk is in Sk, that's why this happens. That does not happen for that. Extremely sorry. This happens because since T with respect to beta, matrix of T with respect to beta is upper triangular, because we had chosen the ordered basis beta such that the matrix of T with respect to beta is upper triangular, and we get hold of such an ordered basis because the minimal polynomial for T splits. Okay, clear? Yeah. So then T, the matrix of T with respect to beta dash upper triangular. So we can now just normalize the vectors in beta dash, and then we'll have our respective our required orthonormal basis. So let me just end the proof here. Normalizing beta dash does the job. All right, clear? Okay. Okay. Now, since we have results related to upper triangularity in terms of an orthonormal basis, our obvious intuition is to establish two diagonalization, and this is the same thing which we did when we had tried to establish the concept that if the minimal polynomial splits, then I'll get hold of a diagonal matrix. Concepts related to that, we had discussed those concepts due to the fact because we had got a very important result which characterized sort of implied the condition of upper triangularity, and that is exactly what we used in this proof as well. Okay, to get into the concepts of diagonalizability in terms of orthonormal basis, let us first see a very important observation. Suppose I consider a linear operator on a finite dimensional inner product space V such that it is diagonal with respect to some orthonormal basis. Okay, let beta be an orthonormal basis for V, and T is a linear operator on V such that the matrix of T with respect to beta is diagonal. But then see, So if T beta is diagonal, then its Hermitian is also diagonal, is diagonal, right? Because in case of considering its sorry, not Hermitian, it's conjugate. Because when we are talking about this conjugate, we are just doing its transpose and conjugate. That will cause no effect to its diagonalizing, to its diagonal structure. So this is diagonal, but then this is simply the matrix of T star with respect to beta. So this is also diagonal, right? Right. But diagonal matrices commute, right? Diagonal matrices commute. So if diagonal matrices commute, then that will surely imply that T and T star will commute. And that implies T star is same as T star T, right? Thus, we establish the fact that if if a vector space, if a finite dimensional inner product space has an orthonormal basis of eigenvectors, because when we are talking about an orthonormal basis such that the matrix of the linear operator in with respect to that basis is diagonal, then that basis is precisely the it contains the eigenvectors along its columns, right? So the basis is typically collection of all the eigenvectors, respective eigenvectors. So therefore, what we have exactly established is that, therefore, um, if a finite dimensional inner product space V possesses an orthonormal basis of eigenvectors, then the linear operator with respect to which we will get a diagonal matrix in terms of this orthonormal basis, it will commute with its adjoint, right? So if I get such a result, then our obvious intuition will be to talk about such operators which commutes with its adjoint. And to like this is an immediate question that whether the converse is true as well or not. Because when we are talking about some observation which seems to be pretty obvious or pretty evident from the structure itself, then the question about a converse is always necessary. A converse in this case which I want to examine is that if I consider a linear operator over a finite dimensional inner product space which commutes with its adjoint, then can I get hold of an orthonormal basis of eigenvectors of that linear operator or not? In other words, if I get hold of an operator which commutes with its adjoint, then can I say that there exists an orthonormal basis such that the matrix of that linear operator is diagonal? Okay. And to do that, we need to study operators of this form, right? Operators of this form are called normal operators. Okay. So definition: let V be an inner product space and let T be a linear operator on V. We say T is normal if T commutes with its adjoint. Okay. And in a similar way, we can also define a normal matrix analogously, uh, an n cross n matrix A, beta real or a complex matrix, is said to be normal if it commutes with its conjugate. Clear? Clear? Okay. Now observe that. Now suppose T is normal. Suppose T is normal. Then T star will be T star T, but that will immediately mean that the matrix of T with respect to beta times the matrix of T with the matrix of T star with respect to beta is same as the matrix of T star with respect to beta times the matrix of T with respect to beta. But then I can write this as the matrix of the conjugate of the matrix of T respect to beta, and so and this as well. But suppose I consider this to be A, then this is A star. So this typically means that A is normal as well. So therefore, talking about a linear operator to be normal is equivalent to saying that the matrix which corresponds to that linear operator in terms of some orthonormal basis is also normal. Here we assume beta to be an orthonormal basis. Orthonormal. Clear? Okay. Okay. Let us talk about some examples. Number one, consider the linear operator on the inner product space R2 such that T is given by let me do it like this. That is basically we are talking about a rotational operator. That is T is the rotational operator, which rotates a given vector by some angle theta, let's say anti-clockwise. So T is the rotation operator. A very elementary calculation speaks of the fact that the matrix of T with respect to the standard ordered basis of R2 is the matrix cos theta. Here you have, I guess, minus sine theta, and cos theta. Okay, this is elementary level math. Just consider the rotation in terms of parametric form, where the parameter comes out to be theta, where theta is the angle by which it is rotated, and then you just take the matrix of it with respect to the standard basis, standard order basis. Clearly, this is an orthonormal basis. Okay, clear. And specifically, we will be talking about the rotation between 0 to pi. Okay, because if we move across pi, then the rotation will be best assumed clockwise. That's a very general notion. The thing to observe here is that if I consider this matrix to be A, then A star is equals to identity, which is equals to A star A. Okay, this you can easily calculate. Okay. Number two is that if I consider any real skew symmetric matrix, let A be a real skew symmetric matrix, then we know that A is same as its the negative of its transpose. Now, when we are talking about real matrices, talking about conjugate is equivalent to talking about transpose, right? Therefore, so A, what is A transpose? It's evidently minus A squared, but I can also write it as A transpose A, right? So this is in fact a normal operator again. The thing to observe here is that T from example 1 has no eigenvectors at all, and that's pretty geometric because we are rotating a vector. We get an eigenvector when the image of that vector under the linear operator is still along the same line of the vector, that because it is scaled by some scalar from the underlying field. But if I rotate a vector by some angle theta which is non-zero, then I cannot get the image of that vector to be on the same line. Hence, it cannot have any eigenvector. Right? If it has no eigenvector, then there is no point of discussing about its whether we get an orthonormal basis of eigenvectors at all. That is, there is no point of talking about a diagonal form of that linear operator. At least, till the tools which we have at this point. Okay. What I'm trying to say is that for a real matrix, because this is a real matrix, so for a real matrix, normality doesn't immediately ensure the existence of eigenvectors. So for the existence of eigenvectors in terms of a real matrix, we need something more, which we will be discussing later. But in case of a complex matrix, We know that in case of complex matrix, whatever characteristic polynomial of a linear operator you start with, it will surely split, right? But that exactly comes from the fundamental theorem of algebra, right? So in that case, we can surely talk about an eigenvector. In that case, we can strictly follow about the fact that if the matrix is normal or the operator is normal, then we can talk about an orthonormal basis of eigenvectors. Okay. So let us now explore a theorem which will actually help us to explore what actually we want to prove in this lecture. Theorem that let V be an inner product space and T is a normal operator. Then we have the following. Number one, the norm of Tx is same as the norm of its adjoint, norm of the image of x under the adjoint. This happens for all x in B. Number two, that T minus Ci, the operator T minus Ci is again normal for all C in coming from the underlying field. Number three is a bit important. Like previously we had discussed the existence of eigenvectors of the adjoint operator when the operator has one. In this case, we can still say the same, but in fact we can say something more. We can directly say a relation, we can establish a correlation between the eigenvalues of the operator and the eigenvalues of its adjoint operator. Okay, so number three is that if x is an eigenvector of T corresponding to eigenvalue lambda, then x is also an eigenvector of T star corresponding to eigenvalue lambda bar. Okay, like we already know that T star will have an eigenvector because T has one, but we can say something more that the eigenvector actually is sort of, you might use the term invariant, because taking the adjoint causes no change in the eigenvector, but it changes the eigenvalue it corresponds to. It changes it to its conjugate. Okay. Number four is that if lambda 1 and lambda 2 are distinct eigenvalues of T corresponding to eigenvectors, say x1 and x2 respectively, then x1 and x2 are orthogonal. That is, eigenvectors corresponding to distinct eigenvalues are orthogonal in nature. Okay. Let's prove this. The proofs are fairly simple. Number one, see, you have if you start with the square of the norm of Tx, then it is surely the inner product of Tx with itself. But then I can write it as the inner product of T star Tx with x. It surely comes from the properties of the definition of an adjoint operator. But I can write it as T star x with x because T is normal, right? Because T is normal. But then I can write it as inner product of T star x with T star x, again following from the definition of adjoint operator. But this is nothing but the norm of T star x whole square. Since we are talking about non-negative values, this implies norm of Tx is equals to norm of T star x. And obviously we are speaking about arbitrary values from V, hence this statement holds for all vectors V, all vectors x. Right. Number two, it's carefully observe that what if I consider T minus Ci times T minus Ci star. So this is precisely T minus Ci times T star minus C bar I. I just distribute it out. I will get T star minus C bar T minus C T star plus the mod of C squared times I. So because I have c times its conjugate, so mod of c squared. And what if I do t minus ci star first? So let me write it as t star minus c bar I times t minus ci, and I'm doing it for all for an arbitrary scalar c. I'll get again t star t minus, I get c t star minus c bar t plus mod of c squared I. But then observe that t star t is nothing but t star, since t is normal. And I can just rearrange these values as minus c bar t minus ct star plus mod of c squared I. This is nothing but t minus ci times t star minus c bar I. But that typically means that t minus ci commutes with its adjoint. So this means t minus ci is normal. Right? Clear? Okay. Let's talk about the third point. So what was the third point? Yeah, third point was that if x is an eigenvector of t corresponding to eigenvalue lambda, then it's still an eigenvector of t star corresponding to eigenvalue lambda bar. How can we prove this? See, we already know that t minus ci is normal for any scalar c. Okay, so let add as given, let x be an eigenvector corresponding to lambda of t. Then t minus lambda I is normal. But then I can talk about the norm of t minus lambda I, the image of some vector v, some arbitrary vector v under t minus lambda I, but that will equal the image of that same vector, norm of the image of that same vector under the adjoint of t minus lambda I. This comes from the first point. So x is also an eigenvector, indeed a vector as well. So that implies that the norm of t minus lambda I x is same as the norm of t star minus lambda bar I x. But the left hand side is 0. So the right hand side is also 0. A norm of something is 0. By definition of norm, the inside must be 0 as well. So this implies that t star x is same as lambda bar x, which means that which actually gives our result. Right? Clear? Clear. Now let's talk about the fourth point. When we say that eigenvectors corresponding to distinct eigenvalues are orthogonal. How can we prove this? Suppose as given in the statement, suppose I take x1 to be the eigenvector corresponding to lambda 1, x2 to be the eigenvector corresponding to lambda 2. I start with lambda 1 times the inner product of x1, x2. Then I can write it as the inner product of lambda 1 x1 with x2. But lambda 1 x1 is nothing but t of x1 with x2. Because lambda 1 is an eigenvector, lambda 1 is an eigenvalue to which x1 corresponds in with respect to the linear operator t. We have not defined it, but that's, you can define it on your own, right? But this I can write as inner product of x1 with t star x2. But since x2 is an eigenvector corresponding to lambda 2 of t, then x2 must correspond to the eigenvalue lambda 2 bar for t star. So this is same as x1 times lambda 2 bar x2. But then I can again take lambda 2 out. So this implies, this is equals to lambda 2 times inner product of x1, x2. Right? But then we get, this implies lambda 1 minus lambda 2 times the inner product of x1, x2 is 0. Right? But lambda 1 is not equals to lambda 2. That's immediately the statement we started with, that if I talk about eigenvectors corresponding to distinct eigenvalues. So this immediately means that x1, x2 is 0. And that is what's exactly what we needed to. Clear? Okay. So now we have sufficient number of tools to prove what I wanted to do, and hence we discuss the theorem now. Theorem. The theorem says that let T be a linear operator where V is a finite dimensional complex inner product space. Complex inner product space what I want to say is that then T is normal, if and only if there exists an orthonormal basis of eigenvectors of T for V, right? The converse part is already proved when we had discussed the observation that if if there exists an orthonormal basis such that the matrix of T with respect to that basis is diagonal, then T is normal. Okay. So in other words, we have already proven the fact that if there exists an orthonormal basis for V which consists of eigenvectors of T, then T is normal. So we just need to prove that if T is normal, then such a thing we can talk about such a thing. Okay. So suppose T is normal. Suppose T is normal. Now since V is a complex space, the characteristic polynomial of V must consider coefficients from the complex field. Hence, by the fundamental theorem of algebra, the characteristic polynomial for T will always split, right? The characteristic polynomial for T will surely split, right? But then, therefore, by Schur's theorem, there exists an orthonormal basis. Say beta. Beta is equals to say V1, V2 till Vn for V, such that the matrix of T with respect to B, let it be A, is upper triangular, right? Is upper triangular. Now see, we have already seen that since T, the matrix of T with respect to beta is upper triangular, this we had seen while we were proving Schur's theorem, then T of Vj, where Vj corresponds to vectors from here, must be in the span of the vectors from V1 to Vj. But that means that T V1 must be in the span of V1. But that implies that T V1 is some scalar multiple of V1. So suppose I write it like this. What I actually mean to say is that this means that V1 is an eigenvector of T, right? Clear? Now we want to establish the orthonormal basis which is containing the eigenvectors of T with respect to the same orthonormal basis which makes the matrix of T to be upper triangular. Okay. So now we try to do that by induction. What we do is that we assume that the vectors v1 till vk minus 1 are eigenvectors of T, and then we prove that vk is also an eigenvector of T. So let v1 till vk be vk minus 1 be eigenvectors of T. We show that the vector vk is also an eigenvector of T. Okay. So what we do is that let j be less than k. Okay. And let lambda j be eigenvalue for the vector say vj. Okay. Then T vj is equals to lambda j vj, but that means that T star vj is equals to lambda j bar vj, right? Right. Now since A is upper triangular, therefore T vk must be in the span of vectors v1 till vk. So I can write T vk as say a1k times v1 plus a2k times v2 and so on till a. So I have this till k, right? So akk times vk. But then if I take the inner product of T vk with let's say vj, Then via distribution, see all the vectors where, see, I get this to be in this form. See, this is basically summation I is equals to 1 to k. See, these ai k's will come out, and I'll be left with the inner product of vi with vj. Right? But this the vectors vi till vj are all orthonormal, so I'll simply get ajk, right? I'll get ajk. I'll get to I will be equal to j. For every other case, we'll have 0 on the right hand side, right? So therefore, ajk can be represented like this, but then that implies that ajk is nothing but vk times t star vj, but t star vj is basically lambda j bar vj, but then I can bring lambda j outside. So this I have lambda j bar, and here I have vk, inner product of vk till vj, but then vk vj will be 0, right? So if ajk is 0, then this implies that t of vk, so ajk is 0 basically for all j not equal to k. In other words, I get t vk is equals to akk vk, which implies that vk is an eigenvector, of t. Therefore, beta, the orthonormal basis beta we started with, is an orthonormal basis consisting of the eigenvectors of t. Right. So this gives us the required proof. Okay, clear? In the next lecture, we will discuss an important example of normal operators, and then we will be introducing the concept of self-adjoint operators after a little bit of motivation that why we require self-adjoint operators, and then we will be proving an analogous theorem like this in case of real matrices. Okay, so meet you guys in the next lecture.